Welcome to the presentation, New Approaches to Zero Liquid Discharge Desalination. I would like to introduce how desalination technology based on drum film evaporators, DFE, can meet the growing demand for fresh water in arid regions through sustainable methods. This technology also contributes to solving various challenges, including agricultural production and lithium extraction from seawater. One of the primary goals of this technology is to protect the fragile ecosystems of warm seas. Unlike traditional desalination, where brine is often discharged back into the sea, DFE systems and evaporative ponds achieve zero liquid discharge by converting all extracted brine into fresh water and solid salts, thereby eliminating toxic marine pollution. Powered exclusively by renewable solar and wind energy, this eco-friendly process supports the sustainability of marine ecosystems and minimizes the environmental footprint of desalination. As global demand for water in arid regions continues to rise, traditional freshwater sources are becoming insufficient. Desalination has become essential, yet traditional methods, primarily reverse osmosis and thermal desalination, have several drawbacks, including high energy consumption, operational costs, sensitivity to feed water quality, and most importantly, environmental risks. DFE-based desalination technology stands apart from conventional methods by relying solely on renewable solar and wind energy for a highly efficient evaporation process, ensuring minimal environmental impact. This innovative approach not only provides fresh water, but also significantly reduces byproducts typically associated with desalination. Let's explore how DFE can help address the global freshwater crisis while promoting environmental sustainability. The DFE desalination technology integrates established devices such as solar panels and parabolic solar collectors with innovative devices like drum film evaporators, DFE, and wind-powered pond evaporators, WPE. All modular components of the desalination system, including the DFE, can be manufactured at standard facilities, transported, and easily assembled. Its self-cleaning heating mechanism allows the concentration of brine up to 500 grams per liter without additional water treatment, simplifying the final drying stage in evaporation ponds and reducing the required pond area. The innovative wind-powered pond evaporators, WPE, further enhance pond efficiency, enabling effective brine processing on a relatively small area without external power sources. The DFE technology provides an innovative way of producing fresh water, relying solely on renewable energy, making it both sustainable and eco-friendly. Due to its simple modular design, DFE desalination plants are easily scalable and require minimal maintenance. Integrated with solar and wind energy, DFE systems directly facilitate desalination. Parabolic solar concentrators generate heating steam for multi-stage evaporation within the DFE, while wind energy completes the evaporation of concentrated brine, reducing dependence on electricity and operational costs. In regions with high solar activity, DFE technology can autonomously produce fresh water and dry salt from brine. Considering the goal of DFE technology for zero liquid discharge, ZLD, toxic brines from desalination plants, which are typically discharged into the sea, can be further treated in DFE complexes. Fresh water is extracted, and the remaining highly concentrated brine is dried in evaporation ponds equipped with wind-powered pond evaporators to enhance efficiency. The amount of water extracted is higher than in reverse osmosis evaporative systems, and the volume of brine directed to the evaporation ponds is minimal, reducing the land area required for ZLD desalination plants. The foundation of DFE technology is the Drum Film Evaporator, an efficient and sustainable desalination solution that evaporates water from brine and concentrates it. Based on devices such as rotary vacuum evaporators, thin film evaporators, and drum dryers, the DFE can be connected in multi-stage configurations for optimal utilization. Unlike reverse osmosis, the DFE uses renewable heat sources for water evaporation, reducing both costs and pollution. Its modular setup ensures scalability and high performance through efficient heat transfer during film evaporation, steam condensation, and the thin, externally reinforced walls of the evaporative drum. The DFE design is engineered for mass production, significantly reducing manufacturing costs. The DFE design is simple and reliable. A drum rotates on bearing supports inside a tube, partially filled with brine. The drum's rotation enables the formation of an evaporative film on its inner surface as it is heated externally by steam. This heating steam condenses and is converted into fresh water, which is then discharged through a dynamic condensate trap. An innovative aspect of the DFE is its self-cleaning mechanism. A spiral rolling belt below the brine level scrapes salt deposits from the inner surface of the drum and transports them to the discharge area, ensuring continuous operation without fouling. The DFE process involves three main stages: steam generation from solar radiation using parabolic solar concentrators, multi-stage evaporation in the DFE, and the drying of concentrated brine in evaporation ponds with the use of wind-powered pond evaporators, WPE. All processes are carried out with minimal environmental impact. Parabolic concentrators collect solar radiation and direct it into a flow channel to generate high-pressure steam required for operating the multi-stage DFE-based evaporative system. This approach maximizes the use of solar energy, significantly increasing the productivity of the desalination plant while maintaining constant insulation power. The modular design and drum film evaporator, DFE, offer the following advantages. Scalability. The modular design of DFE allows for easy adjustment of capacity by adding or removing modules, making it suitable for both small-scale installations and large industrial complexes. Ease of transportation and installation. Each module can be delivered and installed separately, simplifying transportation and assembly at remote sites with limited infrastructure access. Increased reliability and resilience. The system's division into independent modules ensures that the failure of one module does not halt the entire operation, minimizing downtime and enhancing overall reliability. Efficient maintenance and replacement. Modules can be serviced or replaced as needed without a complete process shutdown, significantly reducing repair time and operational costs. Eco-friendliness and energy efficiency. Modular DFE units can be effectively paired with renewable energy sources, such as solar concentrators for steam generation, lowering overall energy costs and reducing emissions. Flexibility for various applications. DFE modules can be adapted to meet specific requirements, including different types of solutions and concentration levels, making the technology versatile for a wide range of industrial uses. This table shows the distribution of thermal parameters across the stages in the modules of the desalination plant during the production of distillate in a multi-stage DFE evaporative system with a capacity of 50 tons of fresh water per day. Unlike conventional desalination, where brine waste is often discharged back into the sea, DFE systems achieve zero liquid discharge by converting all brine into solid salts, eliminating marine pollution. This eco-friendly process supports marine ecosystems and minimizes the environmental footprint associated with desalination. To reduce the area occupied by evaporation ponds, wind-powered pond evaporators, WPE, are proposed, utilizing wind power to complete the salt concentration process in the brine. A special wettable evaporative mesh in the ponds increases the evaporation surface area, ensuring faster and more efficient water removal from the evaporation pond. Toxic brines from reverse osmosis can be used not only for obtaining fresh water, but also for evaporative cooling in greenhouses, creating conditions for a quick return on investment in agricultural production projects through the exclusive use of renewable energy sources and seawater. Due to the dry air, it is possible to cool the initial brine in cooling towers by 10 to 15 degrees, allowing the use of fin tubes with circulating cooled brine as moisture condensers in greenhouses. Excess humidity in greenhouses is created by another system, a fine water misting system that absorbs excess heat in the greenhouse and reduces air temperature to optimal levels for plant growth. The condensate forming on the cooling tubes flows down a channel into a collection tank for fresh water, thus closing the greenhouse cooling circuit without the loss of valuable moisture to the environment. Toxic brines from reverse osmosis can be used not only for obtaining fresh water, but also for providing evaporative cooling in greenhouses creating conditions for a quick return on investment in agricultural production projects through the exclusive use of renewable energy sources and seawater. Due to the dry air, it is possible to cool the initial brine in cooling towers by 10 to 15 degrees, allowing the use of fin tubes with circulating cooled brine as moisture condensers in greenhouses. Excess humidity in greenhouses is generated by another system, a fine misting system that absorbs excess heat in the greenhouse, reducing air temperature to optimal levels for plant growth. The condensate forming on the cooling tubes flows down a channel into a collection tank for fresh water, closing the greenhouse cooling circuit without the loss of valuable moisture to the environment. Here, you can see how evaporative cooling is organized inside the greenhouse. Heated, humid air rises to the upper part where fin tubes with cooling water are located. Moisture from the air condenses on these tubes, and the condensate flows down a channel for reuse. In this way, brine that would be toxic to the sea after reverse osmosis can be used not only for obtaining fresh water, but also for providing evaporative cooling in greenhouses in extremely hot climates. This enables the creation of conditions for a quick return on investment in desalination projects through the production of high-demand agricultural products by using solely renewable energy sources and brine processing. A bit of history behind the creation of DFE technology. Initially, the technology was developed to concentrate liquid radioactive waste for subsequent implementation. However, after solving the problem of salt deposits on the heating surface, the potential of the evaporative apparatus proved to be much broader. Given the scale of applications, the most promising use of DFE technology is for desalinating large volumes of seawater in regions with hot, arid climates, as mass production of DFE will lead to cost reduction and production standardization. Developing the use of DFE in desalination plants will open up opportunities for broader application across various industries, such as chemical industry, purification and concentration of chemical solutions, pharmaceuticals, concentration and drying of heat-sensitive pharmaceutical solutions, food industry, concentration of juices and dairy products while preserving their properties, petrochemicals, processing heavy oils and viscous products, cosmetic industry, processing heat-sensitive concentrates, biotechnology, concentration of enzymes and proteins while maintaining their activity. A group of engineers from King Abdullah University of Science and Technology, Saudi Arabia, has developed a revolutionary method for extracting pure and, most importantly, inexpensive lithium suitable for use in rechargeable batteries from ordinary seawater. To produce 1 kilogram of lithium, the energy cost is approximately $5. Moreover, the further use of hydrogen and chlorine, which are released during the electrolysis process, can easily offset the electricity costs, and the treated seawater can be reused for further desalination. With large-scale lithium production from seawater, a DFE-based desalination plant could become an integral part of this technology. Preliminary assessments comparing the economic efficiency of zero liquid discharge desalination plant projects provide hope for promising prospects in the development of this technology. In conclusion, the DFE desalination plant is a pioneering solution in water treatment and offers a multitude of significant advantages. Sustainable integration. The operation of ZLD brine desalination in conjunction with greenhouses not only addresses the issue of brine discharge into the sea, but also facilitates the production of fruits and vegetables, greening desert areas, increasing oxygen levels, and reducing CO2 emissions. The utilization of recycled plastic in wind-powered pond evaporators plays a significant role in enhancing the ecological state of various regions. Versatile treatment. Capable of treating all chemical compositions, the DFE plant is highly adaptable to various industrial needs. Chemical-free process. The system operates without the need for chemicals, consumables, or special water treatment, ensuring an environmentally friendly process. Energy efficiency. The off-grid evaporation modules operate solely on direct solar energy, converting it into thermal energy without relying on external energy sources. Continuous operation. Thanks to its continuous cleaning system, the plant can operate without interruptions for surface cleaning. Ease of maintenance. The simplicity of operation and maintenance ensures minimal downtime and reduced operational costs. High final salt concentration. There are no limits on the maximum salt concentration in the final solution, making it highly efficient. Low energy consumption. The distillate energy consumption for the evaporation unit is lower than that of reverse osmosis water desalination plants, at just 1 kilowatts per music world. User-friendly design. The plant does not require complicated or expensive equipment, nor does it demand highly qualified staff for operation. Cost-effective production. Mass production of DFE modules will significantly reduce costs, making the technology affordable for various applications.